Thank you all very much for coming. Welcome to your University of Minnesota. And as part of the School of Physics and Astronomy, I want to welcome you to, once again, a summer of Quirky Quantum Physics. Today's speaker is Professor Aleksey Cherman. He received his PhD from the University of Maryland in College Park. He did postdocs at the University of Cambridge, here at the U of M, at the Fine Theoretical Physics Institute, and at the University of Washington. He joined the University of Minnesota in 2018, and he was promoted to an associate professor. We decided we wanted to keep him around for the next 30 years. And on that, looking at his files, they spontaneously gave him the George W. Taylor Career Development Award for Excellence in Teaching. So with that, he will tell us why everything we've been talking about is completely wrong. So if you were confused about it, don't worry. Get ready to be confused at a much higher level. And with that, Aleksey.
All right. Well, thank you, everybody. It's wonderful to be here. In case I have colleagues in the room, I have to start by saying that the title is intentionally provocative. Okay? Particle physicists have not been wasting their time thinking about particles, sort of. I mean, we haven't been wasting time, but what I'm going to try to convince you of is that when we do particle physics, we're not quite studying particles in the way that you would think. And the ways in which that's true are actually very relevant to our everyday life. So my goal today is to convince you of this and try to entertain you along the way. So let's get started. So when we go to school, probably starting in elementary school, maybe even in daycare. I know there's one person here who's still in daycare, my son. We learn that everything is built out of small things. Okay, like Legos built out of Legos. You can see that over there. So for example, if you take this clown, okay, the clown, his book, his hat, his shoes, they're all made out of molecules, okay? And then the molecules, that's the next picture here, they're made out of atoms. And here I'm showing you a truly awful cartoon of an atom. You've probably, I don't quite remember which talks you've seen during this series. But probably somebody told you that this is not really what atoms look like, but let's go with it. And then, okay, so atoms, they have an electron that's doing something around the atomic nucleus, something complicated. But then in the middle of the atom, there's an atomic nucleus. And the atomic nucleus is built out of something called protons and neutrons. And inside those, there are quarks. So like you keep zooming in, and you keep seeing new types of particles. Everything is built out of particles. That's what we learn in school, right? Okay, well. The title is that that particles don't exist, right? So the thing I want to start with is to assure you that particle physics is real, okay? Like it really works. Okay, so what is the job of particle physics people? So, and I'm one of them, by the way. So our job is to first think about particles. I'll clarify what I mean by that given my title in a minute. But anyway, think about them carefully, try to predict what they do, and then use giant machines built by thousands of physicists to see if we're right and try to learn lessons from that. And, well, it all works to just astounding precision. So, so pictured here, the first picture of a field, that's a big particle collider. That's one of the detectors. That's the team of people who built it. And then people like me, theoretical physicists, make predictions for what they should see. And for example, we predict numbers of various sorts. So you see the number on top here. And then they measure what nature does, and that's the bottom number. And don't worry about the numbers themselves, but the thing to pay attention to is they agree to 1 part in a trillion. They agree to 12 decimal places. So we really understand particle physics very, very, very well. So what's the deal with my title, right? Okay, well, I'm going to spend the rest of this 50 minutes trying to answer that question. The thing that I want to highlight is that there are, when we say, anybody, including me, when we say the word particle, see, that word means something in English. And most of us think in English, right? And so we bring in assumptions as we say the word particle, and we picture them in a certain way. So for example, when I say particle, what you have in mind is probably, I don't really have any, okay, yeah, pretend this is a particle. Like, it's an object with a location, like it's here, okay? Well, it stays there if I don't do anything to it, so it persists. It doesn't appear or disappear. And you can separate it from everything else. So it used to be sitting on the table here, and I can take it, I can grab it, I can put it over here. It's fine, right? That's what we think particle is supposed to mean. And the funny thing, okay, is that the things that we study in particle physics, whatever they are, we call them particles, but they violate every single one of these intuitions, these assumptions about what particles should mean. Every one of them. And it turns out that the way in which these everyday notions fail to be true are really important to how the universe works and how our technology works. Okay, so let's see how that goes. So the way that we actually studied this kind of stuff goes by a scary name, which I'm going to try to demystify today. It's called quantum field theory. So let's focus on the field part of field theory first. Well, a field is secretly just a very familiar thing to all of us. We look at one every morning, maybe. So like a weather map with temperatures on it is a field. So it's, it's everywhere, and it takes different values in different places. So here on this picture, the different values are just temperature. How hot is it in a particular place, or how cold? And in this picture, which I found on the internet from like 2025, it's like, how much rain is there in any given spot? That type of information is what is contained in the idea of a field. That's what we call it, okay? But it's a very familiar thing. Now, what does that have to do with particles? Well, you ever seen people doing the wave in a stadium? So think of the location of each person as a little point, and whether they're standing up or down is the information at that point. And you could have ripples in this information. So here people are doing a wave. It's a coherent, all-together motion that just propagates through, even though the actual position of the people didn't change. They just stood up temporarily and sat back down, and it looks like a wave. Well, quantum fields are kind of like that, by analogy at least. They just do wilder and weirder things. The particles that we talk about in particle physics are ripples in fields. And they're quantum mechanical, so they can do weird things. But, so I stole this picture from David Tong, who I think painted it. But, so here you can see the ripples, the particles, fighting with each other. Well, they can interact, right? And some, fighting is a kind of interaction. Okay, so we'll learn a lot more about this, but we got to get some examples first. So first, light is a ripple in the so-called electromagnetic field. It's like a wave of electric and magnetic fields. So radio waves, the wireless internet that we appear to have in this room, and sunlight, which we don't have in this room, at least, no, we don't. They're all electromagnetic waves, okay? And again, I just found some random picture on the internet. Light waves can have different wavelengths. Depending on the wavelength, the properties and how we perceive that kind of electromagnetic wave change. It could be visible, it could be ultraviolet, or even X-ray, or you could go into the radio frequency. Okay, they also have different frequencies, wavelengths, whatever. The thing that is important for this talk is that actually the electromagnetic field is a quantum field. So what that means is that while for some approximations, like for thinking about Wi-Fi in this room, you can pretend that quantum mechanics doesn't exist, at least a little bit. But actually, quantum mechanics most definitely exists, right? It's the summer of quirky quantum physics. And the probability, so basically, quantum fields, including the electromagnetic field, exchange energy with each other in little clicks, in little lumps. even though I just told you the ripples. But quantum mechanics is weird. Okay? And these little lumps of energy that they can exchange, they exchange this energy sort of in a probabilistic way. They kind of roll some dice to figure out who should get which energy. That's the quantum in quantum field theory. And an interesting thing here is that we already, if you take this at face value, you can already see that if you think of the particles that light is made of, these little lumps, they're called photons. And OK, they are particles. I'll try to say in the sense in which that's true in a second. But they definitely are not things that you can pick up and then are just there. They can disappear and reappear. And you can do a very easy experiment to convince yourself of this. Go into a room, turn on the light, all of a sudden it's filled with light. That's just a lot of photons. Turn off the light. The room goes dark. The photons are gone. So, just a fun thing that I learned while preparing for this talk, actually the human eye, the rod cells in our eye, are sensitive enough to fire an electrical signal with just one photon hitting them in a really dark room. Now, our brain filters that information out, because otherwise in dark rooms we'd constantly be seeing little flashes in front of our face. That's totally useless. So the way our brain processes information from our eyes in a dark room, it only pays attention. The thing we can perceive is like bunches of photons. But the actual rod cells, they fire an electrical signal into our nerves, even for one photon. It's kind of wild. You can almost see photons with your eye, although you cannot perceive them without an instrument. Because otherwise, it'd be very sort of evolutionarily bad. We'd constantly be seeing a haze. OK. So just to summarize, a particle is an excitation of a field. It's a little ripple in a field, but that ripple doesn't have to look like this thing, where it's distributed everywhere in the stadium. It can look like that thing, where it's like localized somewhere, but it still moves around and can ripple in complicated ways. OK. So you've probably heard about electrons, right? Well, electrons have something called an antiparticle as well. So for every electron, in principle, there exists something called an anti-electron, which people sometimes call a positron for historical reasons. And both of them are little ripples, excitations, in something called the quantum electron field that is part of quantum field theory. The quarks that are fundamental particles that build up the protons and neutrons inside of atomic nuclei. There's also things called antiquarks. And quarks and antiquarks are both excitations of a quantum quark field. And I've already said that photons are excitations of an electromagnetic field. And so here I'm drawing an electron field. And then I got ChatGPT to take this picture that David drew by hand and do terrible things to it to make it look like that. OK, to make it different. OK, so the idea is the quark and electron fields are different. OK. We got to use the tools of the age, right? OK. So the thing that is worth keeping in mind is this all sounds very fancy, theoretical, not really real, probably. But it's actually, believe it or not, really important to really practical physics. So understanding that particles aren't really things like this at all, and they're actually ripples in quantum fields, is essential to build devices like lasers that might be part of how that projector works. Of course, I'm not completely sure. Maybe not. But lasers are all over the place. There are things like laser pointers. There's an ancient device called a CD player. Some of you are old enough to have dealt with them, and some of you are not. But what happens there is there's a spinning disk, which has little imprints in it, and a laser hits those things, bounces off, and that's how you read music off of it. So we used to listen to music this way. I'm old enough for that to be true. My son is not. Camera sensors. Almost all of us, I think, have a smartphone in our pocket. It has a camera on it, almost certainly. The sensors that record photos on our phones the only way to understand how they work is to really grapple with the full machinery of quantum mechanics, but also like quantum field theory, ultimately. TVs, like, for example, nice OLED TVs. A lot of them advertise that they're using quantum dots to be brighter. Well, yeah, I got to tell you, understanding how that works and making the initial advances that led to this technology was done by people who had to think about the kinds of things that I'm talking about. OK. So that's my pitch for why quantum fields are important. But so far, I've only highlighted sort of like one aspect of the way in which the word particle is a bit misleading. So I want to highlight other ways. That will be the rest of the talk. Just remember that I had another example to try to convince you that all of this stuff is actually useful, that I think is fun. Has anybody here heard of PET scans? OK, so this is not a PET scan. Or more precisely, it is, but it's not the one I mean. OK, if you have cats and scanners at home, they probably like to sit in them because they're warm. And if you activate the scanner, you'll see something amazing that you may or may not want to see. OK, so here it's not too bad. OK, but this is not the kind of PET scan that I'm talking about, because here, actually, I think to understand how the scanner works, you might need to think about things like quantum field theory and quantum mechanics, but never mind that. The PET scans I have in mind are sitting in hospitals. OK? So what the hell is this thing? Well, the PET in PET scan, exactly, it stands for positron emission tomography. Don't worry about the word tomography. It just means basically taking a photo, but in a really fancy way. Now, the positron is interesting. Remember I mentioned anti-electrons? Yeah, the positron in PET scans, it's an anti-electron. It's antimatter in your hospital every day. So how do we get it, and what's it good for? OK, so if you think you might be sick, if your doctor thinks you might be sick, and you need a PET scan, what they do is they give you a dose of basically sugar. OK? But this sugar has some molecules attached to it, or sorry, some atoms that are very slightly radioactive. Not enough to actually harm you, okay, because that's not the idea. But you'll see why that's important in a second. The thing is, cells in our bodies love sugar. So they like to eat sugar. And inflamed or sick or cancerous cells are hungrier and take up more sugar than healthy cells. OK? That's like, people have noticed this, biologists. Don't ask me why this is true. I'm in the wrong department, although I have some guesses. OK? And so what's that good for? Well, so these sick cells eat a lot more of the very slightly radioactive sugar. So this is an image of a sick, hungry cell guzzling sugar. OK? And OK, the radioactive atoms in the sugar eventually decay. And when they decay, all of a sudden, part of the decay is to pop a positron into existence, OK, quantum mechanically. And it wasn't there before, and it suddenly pops into existence. Some other things also happen to make sure that nothing violates some conservation laws of physics. But the point is, you get a positron, and it goes flying out of this atom. And it flies out. And you know, there's a lot of other atoms around, and they have electrons. And the thing the positron wants most in life is to find an electron, ram into it, and turn into photons. They like to annihilate each other. And so the photons, the particles of light, come shooting out of your body and are detected by a camera. And so that's what this machine does. So the image that you see on, which hand is it? On the right, OK? The first picture in gray is done by something called computed tomography, CT scans. That's a fancy pants word for fancy X-ray. That's what that thing is. So everything shows up, not quite everything, but a lot of things show up. The thing in the middle, OK, that's the PET scan. That's the camera seeing where the things that are hungriest for sugar are in your body, and they're not really in your belly. Okay, we're talking about like inflamed tissues. Could be cancerous, could be some other disease. And so they show up as brighter spots. And also check out the brain, right? The brain's real hungry, kind of always, okay? Now, when you put them together, okay, because this machine, I think, also does the fancy X-ray at the same time, the doctors get a really good picture not only of where everything is in your body, but what it's doing metabolically. And that is really useful. And, well, the way it works relies in an absolutely vital way on quantum mechanics and on particle physics. And on the fact that particles can just appear and can just disappear. So, hospitals use quantum field theory every single day. The doctors don't know that. Well, some of them maybe do, but most of them don't. But that's OK, because all they need to know is how to use it. The people who build these machines, they need to know it. OK. So that's the end of the first part of my talk. So now I'm going to move into the next part, which also will highlight the way in which the concept of particles is a bit tricky and slippery. So let me introduce you to quarks. OK? So where do you find quarks? Well, remember I mentioned, OK, everything is built out of atoms. The atoms themselves have an electron and then an atomic nucleus. And inside that atomic nucleus, we have something called protons and neutrons. Those are little particles. The protons and neutrons, if you open a middle school textbook, or maybe high school, you'll see that they are allegedly made of 3 quarks. For example, for the proton, and 2 up quarks and a down quark. And these wiggly things, there's some other particle called the gluon. The physicists have no imagination sometimes. A gluon's role in life is to glue quarks together. OK? Seemed like a good idea at the time, but honestly, I don't have a better one. Yeah, right. So in textbooks for beginners, this is what we say. And it's like sort of true, but mostly totally not. In ways that are like really fun to understand. I mean, if I'm teaching middle school, yeah, I'm going to say this. But if I'm teaching high school, maybe I'll say more. OK, so the funny thing is, OK, so I keep saying, they're quarks. Nobody has ever seen one by itself. And if you have a particle, one of the ideas that we bring with this English word particle is that you can take it and hold it. We've never done this with a quark. OK? So we've looked everywhere, OK? And we have never, ever, ever found a free quark. We started looking for them, actually, before we understood what the heck they were. And we now think that there's a good reason we haven't found them. But when I say we looked everywhere, OK, people tried looking in rocks that they find on Earth, rocks that they found on the moon, oyster shells. This is a weird one that I found on the internet. I don't know. I could not figure out before this talk why oyster shells in particular, but I think somebody had the idea that maybe the oysters concentrate things as they eat them, and maybe there would be more like weird stuff in there. I'm not completely sure, but I've seen multiple sources claiming this. So what we now know, OK, is there's a reason that all these searches for quarks failed miserably in the 50s and 60s and 70s. And that's because quarks are confined. They can never be alone. You cannot separate them from their friends. So there's a picture of a quark catcher who's very sad because he used the particle collider, you can see there, and he totally failed. But he'll be happy later today. So what is, I say they're confined, like what do I mean? So I'll tell you what I mean in a minute, but first I want to give you something which is more of an analogy that is closer to your everyday life. So if you take a magnet, a bar magnet, you could try cutting it in half. And I don't know, you might have heard this before. If you do this, see, if a magnet actually looked like what the top picture looks like, you could definitely cut down the middle and isolate the South Pole from the North Pole, right? But actually, if you cut it, you make 2 magnets, both with the South and North Pole. And you can do it again and again and again, which basically means that top picture is complete garbage, right? Because like, if it was right, you could definitely do it, but it's not. Why? OK, that's actually interesting quantum mechanics and material science and condensed matter physics that, for example, Jim is an expert in. I'm not going to talk about that, but there's something similar for quarks, somewhat similar. OK, so let's see what that is. So coming back to this picture, I said the role of these gluons is to glue the quarks together. OK, fine. But actually, if you look at the mathematical description of gluons, they're very similar to photons. They seem to be very similar. This was actually initially very confusing, because boy, did they not act like photons, despite seemingly being similar mathematically. If you actually try to visualize what the gluons are doing when you take two quarks, a quark and an antiquark, and try to pull them apart, the gluons somehow get squeezed. They don't fill all of space. They get squeezed into a kind of tube that forms between the two quarks. And making this tube costs energy that grows as the tube grows. And this is a picture made by the Adelaide Lattice QCD group using computer simulations. This is a picture of a proton where you have forbidden the quarks from moving artificially. And you just look at what happens if you try to take all three of these quarks apart, and you get this Y-shaped tube. Okay? So for now, it might not be obvious why that's a big deal. But this is what happens. Okay? By the way, I just want to say, like, we know this happens for two reasons. One, experiment. Two, like, really powerful computer simulations using supercomputers. If you ask me to prove that this happens on a piece of paper, or even to give you a good argument, I will fail. And I have friends in the room who work with me and with other people on things like this. This is a notoriously hard thing to understand. We're still struggling, actually, to understand this deeply. But we know it's true. Okay? So because these tubes form between quarks, pulling quarks further and further apart takes more and more energy. The energy that it takes to pull them apart grows with distance. This is very different from the way gravity works or electromagnetism works. Like, electric forces fall off with distance. Gravitational forces fall off with distance. And this is not true for the strong nuclear interaction because of these tubes. It's like a rubber band. You stretch it more and more and more. It's harder and harder and harder to stretch it, roughly speaking. OK, so what actually happens? So you stretch your two quarks further and further apart. You try to isolate one of them. And the gluons get squeezed into this tube that forms, and it gets longer and longer and longer. And the only equation that will appear in this talk, but multiple times, is E equals mc squared. And I allowed myself that luxury because I think, hopefully it's not scary, but like, everybody's heard about E equals mc squared. It's the only one in the talk, OK? So you make enough energy stored in this tube, and at some point, you can convert that energy into mass of other quarks. So what happens is the flux tube, that's what this tube is called, snaps. And you get a quark and an antiquark again. And then, well, they fly apart. And you never get to isolate the thing you tried to isolate. Just make more particles that are like bound up things made out of quarks. So the quark catcher is still deeply unhappy. This is why so this phenomenon that was not obvious how these things would work when we were first looking for isolated quarks, this is why we think we haven't found them. It's because it's very hard to do. It's not really possible with the particles that we have in the standard model of particle physics. Now, how do we know quarks exist if we can't isolate them? Well, there are a number of ways. So one of them is like, if you smash two protons together in a particle collider, they get broken up, OK? And temporarily, OK, the quarks get free, or they think they got free, and they start flying away from each other. But of course, as they do that, the flux tube forms. So let's track one of the quarks. So here it is flying away. There's some other garbage over here that came out of the collision. And there's a tube tying this thing that's flying out to the other collision product. And this thing is flying out really fast because the collision had a lot of energy. And eventually, this tube snaps. And then you get other particles that are formed out of the snapping of this tube, which makes more quarks. And the tube is a little bit unstable, so it actually, as things keep flying apart, it might stretch a little bit again and snap more and more and more. And so what you see is eventually something called a jet, which is like a beam of stuff that came from a single quark that was flying out. And we know enough about how quarks work to understand this process a little bit, enough to convince us from looking at how these these jets of particles are seen in particle colliders, that the quarks really had to be there. This is the very hard science of experimental particle physics. But we still don't see a single quark. Now, you might wonder, like, why does this matter? So in what's left of the talk, what I want to try to convince you of is, OK, this is, at least to me, interesting, but it's more than that. OK? You actually see the consequences of all of this stuff every single time you step on a bathroom scale. So that sounds wild. Let me try to explain to you what I mean. So there's a question you could ask. Any kid could ask it. What is mass anyway? Where does it come from? OK, well, you know, we're made of atoms. They're made of electrons and atomic nuclei, so our mass comes from those. And the nuclei are made of protons and neutrons. Wonderful. So our mass should come from electrons, protons, and neutrons. That's what we're built out of. OK, so now you can weigh electrons. It's a tricky thing to do, but you can do it. And you can weigh protons and neutrons. And again, it's a little tricky. You can't just use a bathroom scale, but we have ways. And you discover that the electron's mass is 2,000 times less than that of a proton or a neutron. The protons and neutrons have basically the same mass. The electrons are way lighter. So that means that even though we're built out of electrons and protons and neutrons, all of them, the electrons, while they're very important for many things, they're almost irrelevant for the question of where our mass is coming from. The protons and neutrons are the heavyweights. They're where our mass really comes from. The electrons are a bit of an afterthought in that. OK, but where does the mass of a proton and neutron come from? Right? You keep going down. Well, here, there's something very strange. Let's go back to atomic nuclei, OK? For just a moment. So remember, quarks are somehow bound up inside of protons and neutrons. OK, but a typical nucleus is built out of protons and neutrons. And if you were to break up an atomic nucleus into its constituent protons and neutrons and weigh them, hi. Thank you for the inspirational hug. So if you were to break up the nucleus into protons and neutrons and weigh them, you get a number. And now you let them combine back in the nucleus. You weigh the nucleus. The nucleus actually has a slightly lighter weight than the protons and neutrons is made out of. The reason for that is that the energy of the bound up atom, the nucleus, is less than those of its constituents. And that's because, again, of E equals mc squared. See, particles like to minimize their energy if they can. They're very lazy. And the energy for something that makes like a bound up thing, it has this shape. So the vertical axis is energy, and the horizontal axis is how far apart the particles are. And basically, it has a minimum somewhere. And that's where the particles like to sit. And in that minimum, the energy is negative. OK, so what does it matter? So that's the energy from getting close together. But remember, E equals mc squared. So if you have a little bit of negative energy, that means you have a little bit of like kind of a negative contribution to the mass from E equals mc squared. So the bound state of protons and neutrons, the nucleus, is a little bit lighter than the things that it's made out of. OK, so quarks completely violate this intuition, like completely and totally. The quarks have their own quark masses, OK? And one of the triumphs of particle physics over the last, really half century is understanding where the masses of the quarks come from. They come from interactions of the quarks with something called the Higgs field, which we only fairly recently, confirmed is really there in experiments, like around 2012, I want to say. But the masses of the quarks themselves, they contribute like 1% to the mass of a proton or a neutron. So the fact that the quarks have a little mass has nothing to do with where the mass of the proton is. The proton is way, way, way heavier than the added up masses of the quarks. So like, how can this be? It's exactly the opposite of the story of the nucleus, which is a little bit lighter than the things it's made out of. Here it's way heavier. What the heck? Well, quantum field theory is weird, okay? So, okay. What's really going on is that roughly 99% of the mass of a proton it's dynamical, okay? It comes from energy. Remember, E equals mc squared again. So most of the energy that's like stuck inside a proton or a neutron, and hence its mass, it comes not from the quarks directly, but from the fact that first the quarks are whipping around inside the proton and neutron at close to the speed of light, and the fact that there are these tubes of gluons connecting them. Now, if you don't let the quarks move, you can't do that in nature. You can do it in a computer. You can put in the interactions and then simulate them and just nail down the quarks. This is what a proton would look like. But real protons, I mean, this is an artistic image. They look more like this mess. So what's going on? So basically, the protons and neutrons, the quarks, they're not standing still. They're zooming around super fast. And as they try to zoom around, these little flux tubes form, and then they break, and then they reform, and then they break, and then they reform. And all of this creates a whole bunch of energy, but the quarks can't fly out, because if they try, then they pay too much energy, and they get pulled back in. This enormous energy stored both in the kinetic energy of motion of the quarks, together with the energy in the glue that's holding them together that's in these little tubes, that energy through E equals mc squared is what gives the mass to the proton and the neutron. That's where the mass comes from. But that means that 99% of the mass that you see when you step on a bathroom scale is coming from the stuff I've been talking about all evening today. It's not from the electrons. It's not from the quarks and their masses. It's from this weird stuff. Can you sit another 10 minutes? So this talk is aimed at a middle school and up audience when I was preparing. So it's a little tough going for a 5-year-old. OK. Right. Now, why do we believe that all this works? OK, well, I already told you. I mean, for example, for the electrons are relatively easy to handle. So we can take the machinery that we've developed to think about all of this over the last 100 years and apply it to electrons. And because they're easy to handle, it's relatively easy to measure their properties. And you go and do it, and you get a prediction that I've already told you is like agrees with measurements to like 12 decimal places. That's the most precise measurement in any kind of physics. Well, at least that I know of. 12 decimal places is hard to get, OK? And understanding how this works is behind, well, most of our modern technology. It's behind how computer chips work. You know, the little circuits inside modern computer chips are only a few atoms wide. So quantum mechanics is like super important at those scales. And the fact that the particles and quasi-particles can pop into existence and do weird things and ripple around, all of that is vital to understand how to make computer chips. So the cell phones that most of us carry, they work based on this stuff. And so the reason I've asked ChatGPT to draw a picture of a happy quark catcher is, OK, he failed to catch quarks, but at least he got a cell phone out of the deal. OK? OK, so I'm running like 10 minutes early. Sorry about that, but maybe that's OK. So do particles exist? Well, I don't know, right? If you think that it's a little object at a location, yeah, not really, right? And if you think of this as a particle, then yeah, it exists. But if you zoom in on it and you see what it's made of, it's just not true, OK? Everything is secretly ripples of quantum fields. The fields can ripple in various ways, spread out, interact, but they're not really little lumps, Not really. If you think a particle just like is there forever, unless you merge it with something, and then you have two particles. Well, again, that's not true. Like the particles, whatever we mean by that in particle physics, they can be created, they can be destroyed, they can pop into existence, and then disappear again. You might think a particle means that it's something that can be isolated. Yeah, that's definitely not true. You can isolate electrons, as it turns out, but not quarks. And remember, that fact is related to where a mass comes from, so it's really not negligible. So the answer to this question of do particles exist actually depends on what you mean by particle. If you mean the everyday definition, the answer is no. If you mean whatever we mean in particle physics, the answer is yeah, sure, why not? But it's because we've redefined it until you can barely recognize it. Okay? But we had to. That's how the universe works. So particles are real, if you mean the right thing when you say that. They're just not the tiny little balls that we like to imagine and that we're taught about when we take middle school and high school classes. They are quantum ripples in fields. So I want to close with this. Okay, you are not really made out of tiny little particles, okay? You are built out of wildly fluctuating ripples of quantum fields. That's what we all are. Okay, let me stop there. Thank you.
Much, Aleksey. That was very entertaining. You know, when you mentioned that this was the most accurate to 12 decimal places measurement in physics, I think it is the most accurate measurement of anything in any field. I was thinking about it, and you were, in essence, by saying to a trillion, you know, to 12 decimal places, is equivalent to measuring the length of a football field with an accuracy of 1 atom. Imagine trying to measure that or to calculate it and to get it to both agree to that level of accuracy. That's what quantum field theory has enabled. Questions? Oh, right over here.
Hi. Good job.
Yeah, hi. So I'm trying to make sense of what you came up here with in your talk. So is it true that loss mass amounts to some energy, and by that same token, we can say loss energy can amount to mass?
Absolutely.
And that, you know, basically the quarks when they are distant apart, they have more energy. When they get closer, they lose energy, and that energy turn into a mass. Is that something one way to?
That's basically right. So it's definitely true that energy and mass are related to each other by this amazing equation, E equals mc squared. And so, yeah, if you can somehow increase energy, then that is related to an increase in mass, roughly speaking. Yes, and vice versa.
Oh, there's a question there. Then we'll wait.
So this is a question about a way to imagine as an analog what a particle is. Would it be not accurate, but okay to think of it as equivalent to a musical note in music?
Good.
And I don't
not quite, but it's not. So okay, it's not that far away. So the musical note is closer to this stadium wave thing that I showed you. But let me think about it. So you can make a sound wave that is actually, you can like, to the extent you can beam sound in that direction, so it's louder over there than over there or over there, that's more like a particle. So it's like a lump. So it's like a wave that isn't all over, but it's kind of directed. I don't know if that's helping, but so it's not too far away. It is a kind of wave. It's a weirdly shaped wave. Okay.
Right. And I did not mean.
So up to that
I didn't mean
subtlety,
literally.
you're absolutely right.
I just mean the way it can be divided into tiny little different frequencies, different. Yeah.
Yeah. It's the analogy is not too bad. Yeah.
Okay.
What is the type of energy called?
Oh, what is the type of energy called? So there are many types of energy. There is energy that comes from moving around like this. That's called kinetic energy. There is energy that is called potential energy. So I get more of it when I stand over here. Right, there's gravitational potential energy. Jim just dropped his keys. So potential energy from gravity got converted to kinetic energy as it moved. There are many types of energy. Yeah.
Oh, that one back there. Okay. Oh. And then we'll...
Hi, I was wondering, in one of your last slides, you said something about color.
Oh.
And
yes.
when it talks to quarks, can you actually explain that?
Yeah, absolutely. OK, so this is another thing where physicists made up a word that we use in everyday life, and it means something completely different. You might be familiar with electric charge, which can be positive or negative. Quarks have something similar, but instead of just being positive or negative, in addition to that kind of label, which is plus or minus, it comes in 3 different varieties. And so people looked at this and thought, OK, what kind of thing has 3 different varieties? And they were like, aha, colors. You can make colors by mixing red, green, blue, right? So they just named this different type of charge that quarks can carry colors. They have nothing to do with color, OK? But it seemed like a good idea at the time in the 60s. Many strange things happened. In the 60s, this was one of them, OK? OK, there's some kids over here who had a question. Yeah.
Am I next? Cool.
Oh, go ahead.
So I saw that beautiful picture of, I think it was the inside of a proton.
Yes.
It looked like nebula and explosions.
Yeah.
And I guess I was wondering, like, anytime there's interactions inside of a neutron, right, between particle or quarks and antiquarks, that sort of thing. I guess I was wondering how such a thing could just hold on to energy without decaying after a while.
Good. The question is, how can these things inside there hold on to the energy without decaying? The thing is, they desperately try to decay. But the things they can decay into are other types of quarks that try to fly out, fail miserably because they're attached by little strings of glue, I guess, like rubber bands, and fly back in, hit something else, that something else tries to decay. That's where that cauldron comes from. Yeah. It's coming from things trying to decay and failing miserably, and breaking up into little pieces, and then those pieces recombining. That's where the cauldron comes from.
Is that a perpetual motion machine, or no?
Well, not in the way that my colleagues would get upset by, but yeah. You can't get all that to do work in a useful way, in the way that you might want a perpetual motion machine.
I had an original question, but I'm changing based off of that. Can this, like the particle mass inside it, can that interact with another proton or neutron next to it at all?
Say that one more time. Just one more time.
So you say it can't do work, so it can't interact at all, even with other neutrons or protons next to it?
Oh, I mean,
Like
it can, but you can't get a free lunch out of it. Let's say it this way. So that's a very deep thing. So I know that there's a couple of kids at the front here and there who had questions, and then people who are older. And then there's a kid who's been very patient right there. Yeah.
So imagine you had an isolated quark without a flux tube or anything. What would it be made of?
Good. So the question was, if you did have a quark without a flux tube attached to it, without this tube, what would it be made of? That's a great question. I actually don't know the answer, because it turns out that that kind of thing just doesn't really exist as far as we can tell. So in other words, if we try to ask this question, the mathematics that we use to try to answer it basically gives us like 0 divided by 0. Like, it just doesn't make any sense. It seems like it should make sense from an everyday perspective. It just doesn't. So I know that's not that satisfying. I wish I could answer you, but I can't. The math doesn't let me. And I have to be honest. So I can't lie about math. Not much.
Hi, great talk. Why do you reckon that the quarks move at the speed of light, or close to the speed of light?
Good. The question is, why do the quarks move at close to the speed of light? That is basically because they're very light, like in mass, And the lighter a particle is, the more it tends to want to move closer to the speed of light. So the best example of this is photons themselves, the particles that light is made of. They're actually massless, and massless things just straight up have to move with the speed of light. So because of these interactions, when the quarks hit each other, and they're very light, they can get boosted to very, very large velocities very easily. And inside of the proton, they're constantly smacking into each other. And so they're just moving around super fast. Yeah, that's the best I can do like on a short notice.
Is it just a matter of energy minimization when when a gluon tube between two quarks collapses and forms two more?
Good. Yeah, at least roughly the answer is definitely. That process of the tube snapping, like really trying to understand it in detail is, like we know that it happens, we know many properties of it. To understand it in detail is a major open challenge that some of us think about, but it's basically energy minimization. That's absolutely right. Just the details are very complicated. Yeah. Oh, okay, over there.
Hello, Dr. Aleksey?
Yes.
How about your education? Where did you come from? Where did you get your PhD? Why did you come here, and any special projects right now?
Okay, so where did I come from? Okay, so let's see how far back to go. I'm not going to get into the biology. So where did I come from? So I was born in Moscow in Russia, but very fortunately for me, my parents brought me here when I was 11 to the US, and I've lived here ever since, almost. So I got my PhD at the University of Maryland near Washington, DC. I went off to the UK for a postdoc, and then came back to the US, and I've been here ever since. Let's see, what else did you ask? Special projects. Believe it or not, there's a person in the room with whom I'm thinking about exactly this thing about how these flux tubes snap. We're trying to understand it better. We have dreams that we can understand it better than people currently do, but they're just dreams for now. We have to work very hard to try to turn those dreams into reality. Yeah.
I didn't even know you could learn this in school.
Why didn't we learn this in school? That's a great question. I think, okay, there are several different answers. So one answer.
You need to come to the University of Minnesota.
Yes, so that's one answer. You got to come to this university, or to some other wonderful university, but you should come to this one. So another answer is, when we first learn something, it's actually very useful to first learn how things work kind of roughly, so we don't get too distracted by all the details. And so that's what people teach in like middle school or something, and elementary school. And then as we learn more and more, we get to understand more of the intricacies, more of the details. And the stuff that I just talked about, it could be taught it could possibly be taught in school. In fact, I think probably in high school somebody should talk about it, but it usually isn't. And usually learn about this stuff when you go to university, like this one. Yeah.
Why doesn't everything disappear? If it's all just ripples, why doesn't it disappear?
Oh, okay, that's a very deep question. Why doesn't everything disappear if it's all just ripples? Okay. So it's because I oversimplified something. Okay, yet again, okay? I told you more of the truth, but not all of the truth. Because I was only allowed to use one equation, okay? Okay, but I'm not going to use more equations right now. I'm just going to tell it to you in words. So yeah, the particles can appear and disappear, but there are constraints they have to follow. They're not completely free to do whatever they want. So for example, electric charge cannot change in this process. So if things just try to disappear, right, the electrons have some electric charge. If you killed all the electrons, that would be bad. You would destroy the electric charge. And the rules for how everything can interact with each other and appear or disappear forbids you mathematically from destroying charge. So yeah, things can appear and disappear, but they have to follow certain rules, and those rules prevent everything from disappearing. That's built into our equations, the ones that I was afraid to show you, and won't. Okay, but if you come to a university, then to be honest, by your third year of undergrad, maybe fourth, you can definitely understand what I just said with the math. If you want. You don't have to, but you can. Okay.
Let's see. Here. Okay, you can give me a hug.
Yes, I was wondering, it seems like a lot of physicists like to think or believe that fields are the actual stuff of reality. And I was wondering if you believe that, or if you believe maybe that they're only a mathematical description of what we know versus what's really happening.
Yeah, okay. Man, we're getting deep. No, because the thing is, okay, you're again catching me in telling you little white lies. I mean, fields are an extremely useful way of talking about what's going on. But one of the frontier areas, sorry, I'm not speaking very coherently. One of the frontier areas in the research on quantum field theory has basically been teaching us that while fields are a useful way to talk about what's going on, they're actually not as fundamental as we used to think. But that's not, there's not a sense in which there's something more fundamental. It's just that, for example, the same physical system can have a description in terms of some set of quantum fields and an equivalent but extremely different looking description in terms of some completely different fields. Which fields are real? I don't know, depends on how you feel like. Both are real, or neither is real. So this concept of fields is spectacularly useful, spectacularly well tested, and yet there are still many mysteries. And those of us who work in quantum field theory have to deal with that, and it's really fun. Actually, it's enormous fun, at least for weirdos like me. But yeah.
Probably last question there.
This is actually a good follow-up to what he just asked. With regard to fields, when we're thinking about them, how far, how wide should we imagine those actually existing? Are they infinite across? And then is the Higgs field, when something suddenly has mass, when it intersects, is the Higgs field, like, should we also think of that as existing everywhere?
Yes.
Or is that separated, and is it moving into where something suddenly is to?
So that's a wonderful question. I should have said the answer to this question during my talk, and I didn't. The quantum fields of quantum field theory are spread everywhere in the universe. That's why everywhere in the universe, when we look in the sky, we can see galaxies that are built out of atoms and protons and neutrons. It's because the fields are everywhere, and the particles just ripples in them. So the Higgs field is everywhere too. Yeah, so they fill all of the universe as far as we understand. Huh? Well, everything is actually secretly four-dimensional. That's relativity for you, but yes. I didn't get into that today, except E equals mc squared. I would have needed a longer talk to tell you about relativity. Yeah.
Well, with that, let's thank Aleksey again. And speaking of relativity, that's a great segue to our final talk next week by Professor Michel Janssen, who will give a history lesson. So he will talk about how physicists grappled with and got up to the point of the Schrödinger equation. So not even the quantum field theory, but just the Schrödinger equation and all the false steps and all he is a dynamic speaker. He is not low-key like Aleksey, but won the Abraham Pais Prize of 2026, the highest award given by the American Physical Society for people who do history of science. Before he started doing the history of quantum mechanics, he was an Einstein scholar. He is one of the editors of the Einstein Letters Project, and he had this great talk on what did Einstein know and when did he know it, and talking about the development of general relativity. And it turns out, that Einstein was deathly afraid of one of the people that Michel will talk about, David Hilbert, a mathematician, that he was going to get scooped by David Hilbert in developing the general theory of relativity. And so he rushed out his theory, and he made a presentation, and he said, this is the theory of accelerated reference frames. And the next week, he gave another talk, and he said, forget what I said last week. This is the theory. And then the next week, he came back and he said, forget what I said last week. This is the theory. And you know the expression, the third time's the charm? Well, it took him 4 weeks. But by the fourth time, he got it right, and he beat Hilbert. And Michel will not talk about any of that. But he has to understand the physics at a very deep level to understand how Einstein was making errors in this development. And he understands the quantum physics similarly. And I've seen this talk, and it is a really entertaining talk to see, because these ideas are just so, I can see in the questions from everyone, so mind-bending, and they were developed by people. The scientists were all people, and the story of how the people came up with these ideas is a fascinating one. So I hope to see you all here next week. And with that, absolutely.
One, if you go back to the previous slide, I promise everybody that Michel is not as blurry in person as he is in this picture. He's completely sharp, and he's a spellbinding speaker.
Yes.
I mean, I've seen him give a colloquium. It is spectacular. I think you're in for a treat next week.
Yes,
Yeah.
Bring your
He's
friends.
way better than me.
We want to see this
Yeah.
place packed.
Yeah.
Bring your friends.
Yeah.
And with that, I just have 3 more books to give away. So look under your seats.